Hello, my name is Manuel and I'm going to talk about computational methods for two-dimensional systems in engineering. Simulation in engineering is increasingly important for solving complex problems, improving designs, or optimizing resources. But how do these simulations work? What is the finite element method based on? This is what we will see in this presentation. Most engineering analysis requires solving complex differential equations, such as heat transfer, fluid mechanics, electromagnetics, or structural analysis problems. The finite element method approximates solutions to these complex calculations so they can be solved with a computer. Let's see what the method consists of by applying it to a structural analysis case, when we want to analyze the stress in a beam due to applied load with respect to the formation of the material. We can do it thanks to the equation of the material strength. This problem can be solved manually since the geometry is simple. The problem arises when we face the analysis of complex bodies. This is where the finite element method becomes a powerful tool to obtain the result we seek. The method is based on discretizing the body into small elements connected by nodes, creating a mesh that covers the entire system. To better understand it, we can see the analogy with calculating the area under a curve. If we don't know how to perform the integral, we can always approximate the solution using trapezoids. The more trapezoids we use, the better the approximation. Mesh discretization follows the same principle. Therefore, the smaller the element, the better the approximation of the results. Although this means that the simulation takes longer to solve. Therefore, are several types of elements, which can be 1D, 2D, or 3D, and have different number of nodes. The use of each type of element will depend on the specific analysis, if it is applying or spatial analysis, or if it is considering simplification like plane, stress, or strain condition. As we see, each type of element has a certain number of nodes that, depending on the analysis, will have a number of degrees of freedom. For example, in a static plane analysis, a bar type element will have 3 degrees of freedom at each node, 2 for displacement in x and y direction, and 1 for rotation. In total, the element has 6 degrees of freedom, described in the nodal displacement vector. This is a simple case, but it can become much more complicated if we take it to a spatial analysis. In this case, our type element has 12 degrees of freedom, 3 displacement and 3 rotation at each of its nodes. The concept of degrees of freedom is very important as it defines the dimension of the calculation. A triangular element in a plane stress analysis has 6 degrees of freedom, or a solid element can have up to 24 degrees. Therefore, 3D calculation usually require more powerful computers to solve. So how do we know obtain the displacement at a rotation in each element of the mesh? This is where the next important concept comes into play, the stiffness matrix, which defines the relationship with the displacement and rotation at the nodes with the applied force. The coefficient matrix is obtained from the equilibrium equation governing the element's behavior. It's complex behavior. Just remember that the method transforms differential equation into a linear matrix. These stiffness matrices are always a square matrix, and their size is defined by the degrees of freedom of the element. However, elements are not isolated. They work together in the mesh. So the next step is to assemble the global stiffness matrix, a matrix that relates all the displacement and rotation of the mesh with the applied force. Let's see an example. This beam has 2 elements, each with 6x6 stiffness matrix, and these 2 elements are defined by 3 nodes with node 2 shared by both. The global matrix of the stiffness system will have an order equal to the total degree of freedom, which are 9, 3 for each node. When then have 9 per 9 matrix, this matrix is formed by the 2 6x6 submatrices of each element which add up at node 2. which is shared. Here we can see that a simple analysis problem already has a dimension of 9 per 9. The global matrix of the system can reach enormous size depending on the element and its degrees of freedom. Thanks to the assembler matrix, displacement at all nodes can be solved, which are our unknowns from the beginning. But to do this, we need to define one last thing. It will be necessary to know the applied force and the boundary condition, which are those displacements that we don't know, such as fixed elements that cannot rotate. With all this introduced, the simulation can be performed, which can take from minutes to hours or days. Once the displacements of the nodes are known, the deformation in all elements of the mesh are derived, and from this the stress are deduced. Obviously, performing this calculation manually is crazy. Therefore, with the help of the computer, the engineering only needs to take care of some stakes. The engineer must be able to define the problem, draw the geometry, introduce loads and boundary conditions, then select the most suitable meshing and understand the result of time to validate the simulation. The simulator will handle with the intermediate states, which are more tedious, such as generating all the stiffness matrices, assembling them, and solving them mathematically. Now we can see as a bunch of examples to a structure to see how the finite element method works, and one example of a plate with a hole inside and how the stresses act in the. In conclusion, using FEM, engineers can solve intricate problems efficiently, ensuring accurate simulation optimizes design. This method can convert complex equations into computationally manageable tasks,